Good evening, class. I am ready to record my last lecture on the nervous system, lecture number 6. So we're going to look at the autonomic nervous system, fight or flight versus rest and repose. That's the plan. All right. All right, here we go. So autonomic, automatic. These are things that happen behind the scenes, really. Your heart rate, your blood pressure, your digestion, all these things that you don't have to be consciously aware of. And when we break it down, looking at the nervous system, somatic, let's take a look here. Pen. Somatic is what we are used to. This is muscles and skin, things that you control in your conscious thoughts. But autonomic, of course, are the other things that you don't worry about, like when you go in a hot tub, the dermal blood vessels dilate, and so it helps you get rid of heat. When you start in the treadmill, your pacemaker of your heart's going to speed up. All these things that are behind the scenes. And I don't really talk, some people talk about an enteric division looking at the guts. I won't talk about that again. But the two we're going to really talk about here are, of course, sympathetic, fight or flight, and parasympathetic, rest and digest, if you will. So yeah, we can separate out all the nerves, your peripheral nervous system. Can be looked at somatic, soma means body, and then autonomic. And then the autonomic, we've got these two competing how do I say this? It's like if you have two different modes, where one is you're really on, you have high blood sugar, you're breathing, your blood pressure is high, and you're ready to go to fight or to run away. And then parasympathetic is the opposite. It's where everything slows down and digestion is more important than being able to fight something. Yeah. And so they have antagonistic effects on organs. So we'll see. Sympathetic is going to speed up your heart. Parasympathetic will slow down your heart. Sympathetic is going to make your pupils dilate. Parasympathetic will make your pupils constrict. Indeed. And of course, you're never just running from a dinosaur or sitting there with chips on you. You can be somewhere in between, but you know that. So indeed, think about your life here and how you are. You're just coming into a test, your sympathetic nervous system, you almost get in a car accident, you feel that adrenaline rush. You got that. Think about it after Thanksgiving dinner. You're on the recliner, your pupils are small, you're salivating, it's going to be parasympathetic is going to be the direction on the teeter-totter you're going to be on. All right, so right now, why don't I just give you the punchline? Why don't I give you the important things about this lecture right here? So when you look at these two systems, you already know sympathetic, fight or flight, parasympathetic, rest and digest. Let's look at the differences. Number one, where do they come from anatomically? You can see sympathetic is going to be coming off your thoracolumbar region, right in the middle, your thorax and lumbar region. And then parasympathetic, you can see we call it craniosacral. See that? Some cranial nerves and then way down some sacral nerves. And in the middle is going to be the sympathetic. Big difference there, right? Number two, let's take a look at this. One thing I want you to notice, I'm telling you it the first time, that these circuits always have two neurons. And we call one the preganglionic, then there'll be a ganglia, and then the postganglionic. So there's always two in a series. And the original nerve starts out in the central nervous system, either the brain or the spinal cord, the nerve cell body, right? And the axon will leave, and then there's a second cell body, and this has to be in a ganglia, because that's the only place outside the central nervous system we have cell bodies of neurons. And so in the sympathetic system, there's a chain of ganglia that come down like a beads in a necklace, that come down either side of your spinal cord and the inside of your vertebral canal, like behind your lungs, stuck to the sides, will be these string of these ganglia. And you see that in the middle, your thoracic lumbar region. And then parasympathetic, the ganglia are out by the organs. They're out there somewhere out farther away. And if you look at the two neurons in series, you can see parasympathetic, there's a long preganglionic fiber. Then the ganglia is out here close to the organs, and there's a short little post. You see that kind of that pattern? You can see it down here as well. A long pre and a short post. On the sympathetic side is the opposite. Usually the pre is very short and it goes to ganglia that are right next to it. And then the post-ganglionic fibers are longer. I'm giving you all kinds of stuff here, aren't I? All right. Lastly, chemically, because this is pretty obvious, is that the chemical, the neurotransmitter with the sympathetic nervous system here at the post ganglionic end, where it's going on the effector organ, is going to be adrenaline, epinephrine, really norepinephrine, noradrenaline, but it's adrenaline, right? And the neurotransmitter for the preganglionic synapse and both of them over in the parasympathetic is acetylcholine, your old friend that you see at the muscle junction, acetylcholine. So chemically, adrenaline is going to be important over in the sympathetic, like fight or flight, adrenaline, right? And acetylcholine is everywhere else. Whew. All right, location where they come off. You can see the pre and post ganglionic fibers differ. And then chemically, yeah. And finally, what do they do? You can see some of the actions. If you're going to be sympathetic nervous system, you're going to be fight or flight, everything. So you're going to have high blood sugar, big pupils, fast heart rates. You don't need saliva. You don't need digestion. You want everything to be focused on what is your enemy and how can you escape, kind of thing. So the bigger pupils, the more you can see, the more it comes in there. Yeah, and of course your mouth dries up, your heart goes quicker, your lungs, the bronchi relax, so you get more air in and out. Yeah, and your intestines are going to be inhibited. Digestion will be inhibited. So it's hard if you eat a big meal that then go swimming, something like that, or exercise, because when you exercise, you got adrenaline, it's sympathetic, and so it's hard because you're fighting against your digestion. You should relax after you eat. Let's see what else. And then blood sugar will go up because fight or flight, man, you need all that sugar so you can run or fight, right? Yeah. And then we'll also see with this sympathetic is that in this case, the preganglionic goes right into your adrenal glands, into the middle, the medulla, and they secrete adrenaline directly into the bloodstream. So like you're almost getting in a fight or almost get in a car accident, you feel that adrenaline rush. It's being released from your adrenal glands and it's going in your bloodstream everywhere in your body, as well as the nerves delivering it directly to like your pacemaker, your heart. Cool. And down at the other end, you can see when you pee, it's parasympathetic. If you're trying to fight, you gotta hold in your bladder. And then sexually down there, you can see sympathetic when you have climax kind of thing right there. But the buildup to it is parasympathetic. So you can see your genitalia have parasympathetic and sympathetic, and then they reverse roles there. All right, a lot of time on this slide. Hopefully you followed along, and if you got lost, don't worry, because the rest of the lecture, I'm going to kind of go through it, just kind of hammer it, some repetition. I'll show it in different ways, but I thought I'd give it all to you right here. All right. Well, here you see that series, always two neurons in a series like that. And again, preganglionic, there'll be a ganglia, then postganglionic beyond it. They always have the two. And this shows it nicely that parasympathetic, the pre is long, the post is short. And sympathetic, the pre is short and the post is longer generally. Indeed. And then taking a look at it, I'm going to look on the somatic side. This is how we know pretty well already. You know that sensory is going to come in. It's going to go on the dorsal side, right? The dorsal root ganglia will have the cell body. And here it's synapsing the interneuron in the spinal cord. And then motor, you all know, goes in the ventral part, right? Ventral is all motor, and it goes out to make the muscle contract. So that's somatic. You're controlling it, control your muscle. Yeah, right there. On the autonomic pathway, you can see it's going to have two neurons in question, that pre and post ganglionic. And the pre is going to start out, here in your spinal cord. And then this preganglionic axon will come out, this fiber. And then here it is synapsing in the ganglia with another neuron cell body. And so you can see, and that will go down to the viscera, to your organs, your heart or your intestines, something like that. Yeah. And of course, autonomic visceral afferent or sensory is going to come in, of course, this way too. And so you're aware of your organs' fullness and things like that too. All right, take a look. Yep, chain of two neurons. Got it? The first cell body will be in the central nervous system, either in the brainstem or in your spinal cord. And the second cell body was going to be in a ganglia. And sympathetic, the ganglia are in this chain. Parasympathetic, they're out close to the organs. All right. And so again, just hammering the same thing. Here, looking at the size of the pre and post, how long they are. I can see sympathetic. I see the ganglia here, close to the vertebrae. So the pre fibers are short. And the post fibers will be longer. And here they are going to the eye to dilate your pupil. All right, on the right, I see parasympathetic. And again, it's going to come off some cranial nerves, these 4 cranial nerves, and then way down in the sacral region to do some lower stuff. So that's a big difference. And then I see that the preganglionic fiber is long, really long, and then the post is short. And if you guys saw I'm sure you saw my lecture. I give it tomorrow again. No, Wednesday for some of you Monday. But the cranial nerves, here's the vagus, number 10. And as I told you then, it means the wanderer, it leaves the head and goes all the way down to all of your guts. And being parasympathetic, it's going to stimulate your intestines and digestive organs. All right. Woo! I keep showing you, these are all very similar, but I'm just hammering different points on here. This really shows where they come off of. And so you can see that the sympathetic is thoracolumbar. That's where it comes off the spinal cord. And here you can see the craniosacral. Sure, you got some sacral ones that are going to go to the end of your colon, your bladder, and genitals, things like that way down there. But then here's the 4 cranial nerves. And you guys have had it, if you studied it, maybe you haven't studied it quite yet, but you can see 3 is oculomotor, facial, glossopharyngeal, and then, and most important, is the vagus. The vagus nerve is parasympathetic, and it goes to your heart, your lungs, your gallbladder, your kidney, your intestines, your stomach, all these things. So it's doing a lot, that vagus. Yeah, and oculomotor is going to make your pupils dilate. Yeah. Here's a view of that sympathetic chain of ganglia that comes down. And the drawing always makes it look better. You can see these beautiful little beads, right? And here's reality. It's more like kind of swellings. See what I mean? But they are in ganglia. They're swelling. Cell bodies are in there. And the other cell bodies are in the spinal cord. And this fiber is coming out into this ganglia where it's going to synapse with another cell body. And then that fiber will go out to your heart, lungs, things like that. All right. Well, if you take a look here, let's look at sympathetic. There's the ganglia. See that chain of ganglia like that? And you can see there's two little roads that connect out right there, called rami. Rami mean these branches or limbs that come out. And we'll see that, remember the cell bodies here in the spinal cord, it's going to come out and it's going to go through one of those ramus into the ganglia. And then it could go down to another level, maybe, who knows? And then it's going to leave out the other ramus to go out to its target. All right. Indeed. And we're going to call these 2 ramus, these 2 connectors. You see them right there? It's going to be a white and a gray ramus. all right? And the white ramus is going to carry the preganglionic fiber, and then a gray ramus carries postganglionic fibers going to their targets organs. And they can go up and down that chain too. And the one exception here with sympathetic nervous system is your freaking adrenal glands, okay? Now the adrenal gland, we'll get to this beginning of next semester because all kinds of corticosteroids come out of the cortex, but we care about this medulla. Medulla is the middle, and the cells are big, and guess what? Those cells in the medulla of your adrenal gland, those are neurons without any processes, no axons, no dendrites, it's just the freaking cell bodies. And the cell bodies are making the neurotransmitter adrenaline and noradrenaline, also called epinephrine and norepinephrine. But so what happens is, and this is the exception, is that preganglionic fiber, sympathetic, goes into these cells, these big cells in the medulla, and then they simply release their neurotransmitter into the air, well, into the surrounding area. And then capillaries pick it up, and the veins leaving your adrenal gland are filled with adrenaline if they've been stimulated. And they wash throughout your body, and you feel it, right? That adrenaline rush, your heart's going fast, you know, your mouth dries up, your pupils get big, you start sweating, you know. So that's that adrenaline that's coming out. And so the cells in the adrenal medulla are postganglionic neurons without any processes. And so they've given their lives to simply making neurotransmitter. And instead of releasing it at the end of an axon at a synapse, it just releases it into the bloodstream. And it has an overall effect instead of a targeted effect. Very, very cool. All right. And once again, looking at sympathetic nervous system, we can see that the first neuron in the two neuron series is in the spinal cord, in the thorax and lumbar region. It's where it comes from, the first one. And then the axon leaves and it hits the ganglia that are along these chains on either side of the spinal cord. And in these chains of ganglia, they're going to synapse with the second nerve in the series, the postganglionic nerve, because then the axon will leave that and it will go to its target organs to do all the sympathetic stuff to get you ready to fight and not digest. All right, I wish, you know, I wasn't talking to a screen, talking to you guys individually. I could look at your faces, see where you're at. But hopefully you're doing well. All right, and so why do we call it gray and white? You should know this, just like gray and white matter. You should know why the butterfly in the middle of the spinal cord is gray matter and why the outside is the white matter. I'm pausing, see, so you can think. The white matter is wiring because of the myelin, the fatty insulation, it looks white. Gray matter means there's cell bodies. It has that Nissl substance that makes it look kind of gray. Yep. And so the white ramus, you can see this kind of bright blue, this light blue. You can follow me here. It's coming out. You can see it's going to be motor. It's coming out this ventral part. It's going to come out of spinal nerve. And then it's going to go in this white ramus because this thing is insulated. It's myelinated. And then it's going to synapse with the second in the series, the postganglionic. And that axon is going to leave in the gray ramus because it's not myelinated. So that branch doesn't look as bright white as the other one. They're all insulated, so they look fatty and white. So the gray ramus is for postganglionic fibers that are generally not myelinated, so they're slower. All right, so parasympathetic, it comes from craniosacral, 4 cranial nerves and down the sacral region. The ganglia are way out by the organs. They're not like close. And so therefore, the preganglionic fibers are long and the postganglionic are shorter. Yeah. Indeed. And cranial nerve, oculomotor, facial, glossopharyngeal, vagus. These are the nerves, cranial nerves. And here's a nice view, taking a look at it. And when we see these pictures, it's the same on the right and left side. We're just showing one side, okay? And again, obviously you can see here's the 4 cranial nerves. Cell bodies will be in the brainstem, and then the sacral ones way down low. And then notice the preganglionic is really freaking long, isn't it? And then the postganglion is really short because the ganglia are out by the organs. They're not right next to the spinal cord. Yeah. So it's going to make this is parasympathetic. It's going to make your pupils constrict. Salivary glands, you can make spit so you can digest and you can chew those crackers. It's going to slow down your heart, constrict your bronchi. You don't need that much breathing. And that vagus nerve is also going to just get your digestive organs, the juices going, get everything moving. Yeah. And this again is just a review slide, so I don't think I'm going to go through it again, except I'll go to the bottom and the fact that sympathetic nerves branch a lot and parasympathetics don't branch as much. Kind of a minor thing. But this particular illustration gets rid of a lot of the clutter, and you can really see that the sympathetic comes from thoracolumbar, parasympathetic craniosacral. God, I think I've said that, 8 times? All right, so thank you guys. Hopefully you got it. And you can see a lot of organs get both. Your eyes get sympathetic and parasympathetic. Makes your pupils dilate and constrict. Your heart gets both. The vagus nerve is going to slow the heart. Sympathetic nerves are going to speed up the heart. Your stomach, the sympathetic nerves are going to decrease stomach activity. And then parasympathetic is going to increase your stomach's going to start gurgling, making juices. Right? All right, so in terms of the chemicals, I've told you before, but if you just take a look here, this NE means norepinephrine, a type of adrenaline. And so you can see it's going to be sympathetic. So if you're giving off adrenaline, it's going to be the postganglionic fibers of sympathetic nervous system. So this is what's going to end up on your pacemaker of your heart, releasing adrenaline. It's going to speed up your heart. You can also, adrenal glands can make adrenaline wash throughout all your bloodstream, also going to speed up your heart. Same chemical. So your adrenal glands, your adrenaline from your adrenal glands, or you get a shot of adrenaline, is going to have an overall sympathetic effect. And then the sympathetic nerves go to targets and release the same chemical to have that effect. All right, and we call these fibers that secrete adrenaline adrenergic adrenaline. And ones that secrete acetylcholine, cholinergic, like acetylcholine, cholinergic. So if you're a cholinergic fiber, you know it's secreting acetylcholine. Adrenergic adrenaline, it's just going to be sympathetic, the post. All right, so this does a great job of summarizing again, this figure here. This is what we were used to before the nervous system. This is with the muscular system. So see the big old motor neuron? You see it's beautifully myelinated, the Schwann cells, and it's secreting acetylcholine. And it's going to make that skeletal muscle contract, right? It's going to begin it. Today we're talking about autonomic nervous system. And I guess we can start parasympathetic. You can see here is the first neuron in the series. You can see the preganglionic fiber. You can see it's myelinated too. See the little cocoons along it. And it's going to release acetylcholine in the ganglia, which will be out by the organs. And you see the postganglionic, see that dotted line? Not myelinated. And that's going to secrete acetylcholine again. These are both cholinergic fibers secreting acetylcholine. They're going to have parasympathetic or resting and digesting effects. All right. Now, sympathetic, fight or flights. And I'll start here with there are cell bodies in your spinal cord that are going to fire when you need adrenaline, when you're in a fight or flight situation. And you see the preganglionic fiber is going to go to the adrenal medulla, and it's going to cause it to release adrenaline into the bloodstream. So your whole body is awash with this neurotransmitter if you get your adrenal glands and squeeze the middle of them. Yep. And more normally, the rest of the sympathetic nervous system, you can see here's the preganglionic fiber, pretty short. The ganglia is right next to it. And then here, acetylcholine. But you can see the much longer postganglionic fiber, bam, adrenaline's given off at the end of those. So that's an adrenergic fiber, secreting adrenaline. All right, how am I doing? This lecture, there's certain things I keep hitting on so you know the difference between the two. Yeah. All right, and then we get a little bit into the weeds, but I just want you to, because you may run into this, any pharmacy type people, you're definitely gonna run into this, but cholinergic, acetylcholine, we talk about two types of receptors, and nicotine actually is gonna bind with it, and muscarinic, that mushroom muscarinic, it's a toxic mushroom right there. They're just slightly different, acetylcholine receptors. The nicotinic are a little faster, so you're gonna see like on a muscle. And then the adrenergic receptors mean the receptors for adrenaline. And you have two types, alpha and beta. So you have alpha and beta receptors, adrenaline receptors. And yeah, I think I'll leave it at that for now. Then we'll talk about the difference between adrenaline and noradrenaline. Yeah, and I really don't feel like getting it too much, but you can see here that parasympathetic, it can take the slower muscarinic down here, but yeah, and then here it shows adrenaline has an alpha and beta receptor. So adrenaline can go on alpha or beta receptors, and then different blood vessels and your pacemaker, your heart, they have different proportions of alpha and beta adrenaline receptors too. It allows some fine tuning. And one more time, this is similar to an early diagram, but you can see here, sympathetic nervous system. Here's the preganglionic neuron, cholinergic, secretes acetylcholine. And then you can see, I'm sorry, this is parasympathetic. And then the postganglionic, also acetylcholine. And then you can have a pretty slow receptor on this end. There's not a big rush. Stomach, digest, the big rush is muscles contract, reflexes. When you're doing sympathetic, parasympathetic is resting and digesting, so you don't need the quickest effect. And on top of sympathetic nervous system, and here you can see that the first fiber, the preganglionic, is cholinergic. It releases acetylcholine, but the postganglionic neuron is going to be an adrenergic fiber because it's secreting adrenaline. And then you have on the effector organs, like your pacemaker, your heart, or your gut, anything, you have receptors for adrenaline, and it'll have that effect. And again, the adrenal gland is a special case. It doesn't have postganglionic fibers. It just has a pre, and then the cells in the adrenal gland are the postganglionic neurons, but they don't have any processes. All right, so we'll review. So here we don't need to get into it, but you do have two very similar chemicals. You can look, they come from a precursor dopamine, talked about as a neurotransmitter in the brain. Yeah, and you can see, look at the chemistry. Oh my God, just have a methyl group. I'm going, if I start talking about organic chemistry, just, there's a problem. No, I did take organic chemistry. I passed organic chemistry. But here you can see slight differences between these two, and they bind differently to these alpha and beta adrenaline receptors. So again, it's synonymous, epinephrine or adrenaline, norepinephrine or noradrenaline. You can use either one. You hear me using them both, right? Yeah, and so the difference between these two, why do we have two different ones? There are different proportions they're released. It gives us some fine control. And so you have situations where adrenaline can have different effects on different blood vessels. The muscles, adrenaline is going to open up those blood vessels and the brain to deliver blood for running away and thinking, right? And it's going to constrict blood vessels to your gut, where you don't want the blood going there. You got to shunt it away to keep blood pressure high elsewhere. And so you can see how adrenaline can have different effects on different organs depending on the receptors and some of these fine points. Oh, and you wonder why, if you're allergic to bee stings, why you carry an EpiPen. And you do it because if you have an allergic reaction, an anaphylactic reaction, your bronchi are going to close up. So adrenaline causes those bronchi to relax. It allows you to breathe and survive in some cases, right? So that's the deal with an EpiPen. It's just filled with adrenaline, and it will counteract the effect of constricting bronchi, not being able to breathe. Increase your blood pressure too, other things. All right. All right, you guys are very patient. We're almost there. So you know that a lot of your body has this dual innervation. So your eyes, your pupils, when the sympathetic nerves or adrenaline hits them, they are going to dilate. Light too, light of course, but this is just the effect of adrenaline. So if you guys are scared, your pupils get big. I should mention too, why not? Your pupils, if you like someone, if you're attracted to them, your pupils dilate. So it's kind of a tell. And it's thought to be attractive back in the, way back when, the Mona Lisa, if you look at the painting, the Mona Lisa, the pupils are dilated, and they would put drugs, atropine, to make your pupils dilate, to make you more attractive. So it's kind of a sign. It's subtle, but yeah, you can look for that. All right, where am I going to this? And then the other innervation, of course, is parasympathetic will cause it to constrict. And so you have dual effect on that. On your heart, same thing. Sympathetic will speed up the heart. Parasympathetic will slow down the heart. But I want you to know this case. There's not always the case, dual innervation. Blood vessels, they are only going to have sympathetic, not parasympathetic. So the sympathetic nervous system is going to either, there's a lot, in certain cases, a lot of adrenaline, or it's going to constrict the vessel. And if there's less, it's going to allow it to relax. So you can see in here, instead of having like a gas pedal and a brake pedal, you just have a gas pedal. Either you put it on, a lot of gas, or you pull off the gas. And so that's the way that's done. And blood vessels, I also want you to know, always you've got this partial contraction. If they were all to relax, you would just drop dead. Your blood pressure would go to nothing. So your blood vessels are always have this tone. It's called this blood vessel tone, or sympathetic tone. Yes. And you don't have to get into this. I don't talk about this here too much. You can look at it. One last time. You think it's true? I think I'm just going to tell you one more time. I think so. I think we've hit it. But this is also putting it all together. Remember, somatic, like in your muscles, acetylcholine receptor on the muscle causes it to contract. Bam. There's just one motor neuron. Autonomic, two neurons in a series, right? A pre and a postganglionic neuron, right? And all of them, that preganglionic uses acetylcholine. The difference is the neurotransmitter down in the sympathetic is going to be use adrenaline, whereas the parasympathetic sticks with acetylcholine all day long. All right. And to put things together a little bit, again, I tend to talk about little pieces, but let's look at your blood pressure in your heart. So we're going to have in your carotid artery and in the arch of the aorta these baroreceptors that measure pressure. It's measuring your blood pressure. And it's going to be carried back through sensory or afferent fibers to your brain. You're in your medulla oblongata, where there's a cardiac center, a cardiovascular center, that is measuring your blood pressure constantly. When you stand up from a chair, your blood pressure drops, right? And if you're really worked up, your blood pressure gets high. And so it's always being sensed by this cardiac center in your medulla. You can see it's carried by glossopharyngeal and vagus nerves carried in. And then you have a vagus nerve that comes out, and the vagus nerve is going to go to the pacemaker of the heart. You're going to see this SA and AV node. We'll get to this next semester. But these are the pacemakers, that how fast your heart rate is. And with the vagus nerve, it's going to slow down your heart. Yep. And it's this feedback. If your blood pressure is too high, you're working on the treadmill, your blood pressure is getting dangerously high, the vagus nerve will come down and try to, if you slow the heart rate, you slow the blood pressure. It's one way. And then sympathetic, let's say like your blood pressure is too low, it drops. And so you need to get the heart going faster and harder. You'll have a sympathetic nerve. Look at it going to that ganglia there. Beautiful. And sympathetic nerves will go to those pacemakers to speed up your heart. And there's also fibers that go to the muscle itself that make it contract harder. There we go. We got sensory coming in, motor coming out, that dual innervation. So your heart, the heart rate is always, fine-tuned to your blood pressure and your needs. All right. Well, these neurotransmitters have to be broken down. or else they will constantly be stimulating, right? Let's say you have a fight or flight reaction, and then, you get past the issue. You can't like always be up, right? You got to like break it down, slow it down. So acetylcholinesterase, that was on the last test. It could be again, is it breaks down acetylcholine. And then interesting, the adrenaline lasts a little bit longer, especially the adrenaline from your adrenal gland versus from the nerves. It tends to hang around longer. So you feel that adrenaline rush, right? And it kind of stays with you. You have the, for minutes afterwards, you still feel, that adrenaline. So interesting. So the adrenaline has to be taken out and recycled, but it's slower than the acetylcholine is broken down quicker with that enzyme. All right, and I'll show you how you can fool with this, really. There's pesticides called organophosphates. And again, being from Iowa, you have this thing called atrazine. It's put on the corn and soybeans. Here in Maine, we grow, potatoes and trees. We don't use as many pesticides, but on the Midwest, it's a big deal. And these pesticides screw up the nervous system of animals and people. I mean, they can. There's some really nasty ones. And how they actually work, let's take a look. So here's normally acetylcholine is released. Here's the receptors. And so this cell that axon causes the next neuron to be excited. Now, you can have the stars are the enzymes that break down acetylcholine. And so normally they get broken down. And so the signal goes once. But here, look what organic phosphates do. That's going to be the red triangles. They bind with that acetylcholinesterase and they make it ineffective, so it can't work. And so now this thing is like stimulated constantly. So that's a way that a pesticide can disrupt the nervous system. Yeah, not good. All right, so your autonomic activity, this parasympathetic and sympathetic, you don't control it. I mean, you can consciously think of things that are upsetting and you can cause your heartbeat to increase, but normally you don't. You just go with the flow, you react to your environment. So it's your central nervous system, brain and spinal cord. And there can even be a little bit of independence because there's cell bodies in your ganglia. So you have little brains, scattered outside your central nervous system too, a little bit. Your medulla is the base of your brain stem, and that controls really basic things like your breathing and your heart rate. So at the very base of your brain. Again, this is review. Hypothalamus controls a lot of your visceral functions, your thirst, your hunger, your temperature. All these things are measured in your hypothalamus, which is in your diencephalon. And then don't forget your limbic system has to do with your emotional responses, right? And so your limbic system, I talked about olfaction, smell goes right into your limbic system, and it can cause a rush, a change in your brain chemistry, and all these things can happen like that. All right, for you pharmacy people out there, look at drugs. Cholinergic drugs are going to mimic acetylcholine, and so they're going to have parasympathetic effects. So if you need someone to maybe get their digestion going a little bit or slow down their heart, give them cholinergic drugs, and they will act as parasympathetic mimics. And and agonists mean this, they're helping. Like an antagonist is the enemy. Agonists are helping. So these are going to mimic acetylcholine and have the same effect. Or indirectly, you can just inhibit the acetylcholinesterase so that the acetylcholine hangs around longer and has more of an effect. So either way, acetylcholine is having more of an effect, and you're doing that stuff like saliva and tears if you can't do that, or digestion, stimulating that, right? Yeah, it's gonna, if your heart rate's too high, give a cholinergic drug, it's gonna lower your heart rate. Yeah. On the other hand is giving adrenaline, like that EpiPen. Adrenergic drugs are going to have sympathetic or adrenaline-like effects. Yeah. This is from the movie Pulp Fiction, a real old movie, so I don't know if you guys have seen that. But if your heart stops, you can get adrenaline, put it right in the heart, and it can sometimes bring you back to life as it did in the movie. Yeah. Ephedrine, that was used as a weight loss thing. And then it was taken off the market. It was dangerous, and then it was allowed. So I don't know where it's at right now, but these things have sympathetic or, adrenaline-like effects. All right. All right, we got to the last slide. So hopefully, you guys got the basic points when we talk about these two systems, sympathetic and parasympathetic, part of your autonomic system that keeps this balance that I talked about, the differences. Yeah, all right. We are done with the nervous system. This was a big one. Complex, right? But look at that lifespan changes. What happens to your nervous system as you get older? Well, for some elderly people, they retain beautiful cognition, clear memory, no problem. But many have dementia, right? Memory loss, dementia. So it just varies on the person. But over time, your brain does shrink and you tend to lose the gray matter as it goes along. And you can see, look at this, by age 90, the frontal cortex lost half its neurons. Yeah, that's a lot. Wow. Yeah. And yes, so memories can fade as you lose neurons, as you lose connections. What certainly happens is that with your nervous system slows down, your reflexes slow down. So elderly people have more falls because their responses are slower, and so they tend to fall. And unfortunately, if you have osteoporosis, there's more broken hips, things like that, definitely. And then, with age, I guess the one thing, the nervous system is you gain wisdom, right? At your age, you don't have as much life experience behind you as someone that's older. And so wisdom does grow, but your brain is shrinking. You forget of it. You forget some of that as you get older too. And then I remember I talked about sleep. The problem is your sleeping patterns too, as you get older, get disrupted. So grandpa, gets up in the middle of the night and can't sleep, as soundly as can't sleep like a baby, that expression, babies don't sleep that well, do they? I don't know. They get up, they cry, right? Yeah. All right, so nice. We got to the end of this nervous system. Whew, we've talked about a lot over the last few weeks, haven't we? From just action potentials and how the cell neurons work, to the wiring, whether it's insulated or not, to the parts of the brain, to subjects like memory, to finally your nerves and looking at how your body reacts to rest or to be ready for a fight. All right, so this is chapter 10 we did before. This is chapter 11. Yeah. All right, any last words of wisdom for you? Study hard. We'll have an exam, chapter 10 and 11, and it'll be, I think it's 50 or so questions looking at both chapters 10 and 11, picking out these major points. So from this last lecture, know that there's two neurons in a series in the autonomic nervous system. Know parasympathetic and sympathetic, those like about 4 distinctions I talked about, and you'll be in good shape. All right. Hope you guys enjoy the lecture and study hard.